All right, so this is atomic orbitals and quantum numbers. Technically, it's part 2 because I did make a part 1 for the other section, but this is going to be a quick overview on exceptions to electron configurations, as well as atomic orbital shapes and quantum numbers. Okay, so obviously we have our periodic table here, and the first thing we're going to do is just quickly talk about electron configurations. Okay, so in terms of this, what I'd like for you guys to do is take a second, and we're going to do chromium. All right, we're going to do chromium's electron configuration. All right, so we're going to say chromium, and we're going to go. I like to start from the beginning, but then we can do the shortcut in a second. So remember, this is 1, 2, 3, 4, 5, 6, 7. So we're say 1s2, right, counting helium. So that's 1s2. Then we jump down to 2s2, 2p6, right? This is 2s2, 2p. I'm going to go through all 6 boxes, right? Because this is p, this is s, this is d. Then we go down to 3s2, which is right here. 3p6, 4s2, and now we're into the D, okay? So we're going to go to D4. But the issue here is that we need to remember that the D block, okay, this whole D block here is off by 1 energy level. That's just the order with which the energies that they go. And so this is actually 3D, 4D, 5D, 6D, right? 1 off from the number on the left-hand side. So this is going to be 3D4, okay? Now, we can use what's called noble gas notation if we want to, which would mean we find our chromium here, and we go backwards until the first noble gas that we hit, which is this column here. In other words, something in column 8A. Those are called the noble gases because they're completely filled with their orbitals. So I go backwards and realize that argon is the first noble gas that I hit. So I'm going to start with that. So I'm going to say brackets, argon, which is implying like everything up to argon. And then I'm going to start from argon, which would be 4s2, 3d4. Okay? So if we were to check our work, right? This whole section is argon. So I'm just going to simplify that and write argon, and then 4s2, 3d4. How do we tell if we're right? We add up all the exponents and make sure it equals chromium's atomic number, right? Which is 24. So if we add up all our exponents, this equals 24. Same thing, this would be 24. Same thing down here because we have 4, 2, so that's 6, plus whatever argon is, which is 18. So that also is 24. So we can just double check our work and make sure that we are correct, okay? So that is what I would expect for you to draw for chromium, okay? Here's the thing. Chromium is an exception. As you're going to find out, there's exceptions to pretty much everything. And so it is an exception. And I'm going to tell you why. So atoms want to be stable, right? And so atoms are most stable when all orbitals are full, okay? So in other words, there's electrons in every situation. Or if you're thinking like the hotel analogy, all the beds are full, right? All the beds are full. So that's the most stable situation. If you can't be totally full, because obviously, you know, most of the elements can't be completely full, just given where they are on the periodic table, what we find is the next best thing, or next best for stability, is to be half full with orbitals. Okay? So let's draw out chromium. I'm just going to draw out the outside energy levels. So we would have one box for 4s. Now, 3d, okay, D, if we come back up here to the periodic table, D, in this D section here, there are a total of 10 elements per line. 10, 10, 10, and so on. So in other words, there's 10 electrons here. 10 electrons. Just clean this up a little bit. Okay? So there's possibility of 10 different electrons here, which means if they're allowed to double up, which we know they are, that means there's 5 possible bunk beds. Right? Just like over here in the P section, there are 6 electrons, which means there's 3 possible beds, bunk beds. Okay, so for chromium, the way we initially did it would be like this, 4s2, 3d4. So this is not ideal. Even though the 4s is filled up, right, that's good, the 3d is not full, nor is it half full. And so what we actually see happen in chromium is that this electron, we bump up to that spot, okay? And so what we end up with, if we just kind of re-sketch this out real quick, if we redraw this, we end up with half full all the way across the board, or 4s1, 3d5. And this is the way we actually encounter chromium in the real world. Now, if you were to look at this kind of on paper, we would look at this and say, well, this is an excited state because this is violating the Aufbau principle. Okay? So what we need to look at here is understanding that the 4s and the 3d or sublevels are actually pretty close in energy. Because remember, as we progress out from the nucleus, those energy levels actually get closer and closer together. So it becomes easier and takes less energy to move. So the increase in stability that we gain from being completely half full, in other words, this here, right? The actual increase in stability or decrease in overall excited energy is enough to overcome the amount of energy it would take to bump this guy up, okay? And so we see that with chromium. So chromium's ground state is actually that, with argon in front of it, okay? So that's an exception. And it's because, in terms of stability, half full is good. So let's come up here. Can we think of another element that might have a similar situation? And hopefully you're thinking about this guy right here, MO, right beneath chromium. So it's going to basically have the same exact electron configuration, right? Same pattern. It's just going to be one energy level higher. So instead of 4s and 3d, it's 5s and 4d, but it's the same setup, right? And so MO's configuration is going to be, if we go backwards, krypton, 5s, it should be 2, 4d, 4, but what we actually see is this electron bumps to here, so it's 5s1, 4d5, okay? So in theory, you would expect this whole column to do it, right? Now, that's okay to think that way and to predict that way. It gets a little messier when we get down to these guys, because now we're mixing in the F block, right? Because the F block is actually like right in here and right in here, and so it gets a little bit trickier at that point, but it's not a bad kind of mindset to have, that whole row under chromium will do this. The other elements that will do this, or something similar, is copper and copper's row. So think about that. think about where copper is. Okay? Copper's right here. So we have, in theory, we would write copper 4s2, right? After argon. Argon, I should write that down. Argon, 4s2, 3d9. Right? So similar thing. We want to be full or half full, right? Or a combination of that. So what we can do is bump one of these to here, and we end up with 4s1, 3d10. So the D is full, all 10 beds are full, and the S is half full, right? So if we were to come down to our diagram here, right, it would look like that, because we would take the one that should be here and move it over there. Okay? And now we're full / half full. So those are some exceptions, right? Again, it gets really messy down here in the F block, okay? So I'm going to show you one of the F block, and then we're going to get into the quantum numbers. Okay, so let's do promethium, PM. Now, just like the D block being off by 1, the F block is also off by 1. So if we have, 3, 4, 5, 6D, right, what we also have is 4, 5, F, right, because this would be 4, 5, F. So the F block is off by 1, and that will hopefully make sense in a little bit, okay, as to why. Okay, so let's do PM. Okay, so if we look at where it actually is, think about this, like what row is that actually in? If we put the F block back into the periodic table where it's supposed to be, PM is in row 6. Okay, so I'm going to go backwards and start with xenon. So I'm going to say xenon 6s2, right? I'm going to go through these guys, okay? And then I have a situation. This element right here, okay? Just clean this up a little bit. This element right here, it has to be an element. Something has to be there to take that spot, right? And so that is actually lanthanum. So lanthanum goes here, and actinium goes here. Depending on what kind of periodic table you have or what you're looking at, you might see them there and not here, or you might see them here and not here, or you might see them actually written twice, repeated, okay? And that's because there's a lot of exceptions that get in this area. And so the lanthanum and the actinium could be kind of anywhere. But right now we're going to assume they're here, okay? And so in reality, okay, F starts here, not here. These are part of the D, okay? So F has a total of 14 boxes available to it. So it's 6s2. I got to go through lanthanum, which is 5d1. After lanthanum, I go 1, 2, 3, 4 into the F. So it's 4f4, right? D is one level off. F is one level off from that. And if I want to double check and make sure, I add up all my coefficients, or all my exponents, right? And so if we come up here, right, xenon is number 54. So that would be 54 plus 2, 1, and 4, right? So that's plus 7, right? Which should give me 61, which is PM. So this is one option for PM. As I said before, it is possible that there are some exceptions and that this lanthanum element could kind of be in the F if the F is not full. So another way that you could do this, that you could write promethium, is xenon 6s2, 4f5. In other words, I'm now counting this 5d1, this lanthanum element, I'm now counting it in the F and just putting that together. Both of these are okay and acceptable because there are so many different exceptions, I'm not going to make you memorize those. Okay? So that's the gist with the F block ones, right? So it could be either of those, okay? And we'll practice more of those as we go forward, but that just gives you a good sense, okay? All right, so now we're going to start thinking about what all these numbers mean and so on. So in order to classify electrons, we have 4 kind of ways that we do that, right? We start broad, and we just say energy level, right? Like 1, 2, 3, etc. Okay? Then we have, okay, what sub-level is it in, right? So energy level is like the row on the periodic table, if you want to think about it that way, right? Then we have, okay, well, now we know, you know, what row is it in, but then we want to know, okay, what section? Is it S, P, D, or F? Right? Then once we know what sub-level it's in, we need to know what orbital it's in. So these are like the boxes in the diagram. Oops. Or you can think about it as the bunk beds from the analogy, right? And then the final differentiator is spin. So if they're in the same energy level, the same sublevel, the same orbital, then they have to have different spin, because no 2 electrons can have the same set of 4 of these coordinates. So we say spin up or down, right? Okay, so those are our options. So what we've done is we've actually converted these to numbers so that we can actually talk about electrons specifically, okay? And so here's what we did. So these are called the quantum numbers. And there's a great, I think it's Key Concept 8.5 that you can watch in the textbook that might clarify this as well once we get finished. So the first quantum number that we're going to call is the principal quantum number. And we call that N. Okay? And that's going to be numbers 1, 2, 3, etc. based on row in the periodic table. Right? So that's the easy one. So that's one. Second one is called the angular momentum number. And we call that L. We always write it in cursive just so it doesn't get confused with an I. Now, L, the value for L, so, sorry, I should have said that this is N equals, just so we have a sense there. Okay, so L equals 0 to N minus 1. So in other words, there could be multiple values for L. Okay, so if we have something in row 1, energy level 1, right, N equals 1, that means that L is going to be 0 because N minus 1 is 1 minus 1 is 0. If I have something in N equals 2, L could be 0 or it could be 1. If I have 3, it could be 0, 1, or 2. Now, it's not a coincidence that whatever the value of N, that's how many values of L we should see. So L corresponds okay, to the sublevel, as in S, P, D, or F, okay? All right. Sorry, phone's ringing. Okay. Okay. So that corresponds to S, P, D, or F, okay? Okay. Now, whatever the value is, okay, it corresponds to a letter. So for example, if I have n equals 1, right? N equals 1. That means, where are we on the periodic table? Right? We are here, 1. How many possible sublevels are in n equals 1? In other words, S, P, D, and F. Well, there's only S in 1. So I should only have one possible location for the electron. If I'm in row 1, all I could be is in S. So I should only have one solvable value. But what happens when we go down to row 2? Right? I could be in 2S, or I could be in 2P. So I should have two solvable values, which we do. What if we get into row 3? I could be in S, I could be in P, and don't forget that this is actually 3D. So I could be in 3 possible locations. What happens when you go to 4? I could be in S, I could be in 4P, I could be in 4D, or I could be in 4F. 4 possible locations. Okay? And so these values correspond here. So if I'm in n equals 1 here, that means my L is 0, which means I'm in an S orbital. So S corresponds to 0. P corresponds to number 1. D corresponds to number 2. F corresponds to number 3. Okay? So that's the second one. Third one is the magnetic quantum number. Call this one M sub L. Okay? And this is based off of the orbitals, right? So like, which box is it in? The values for M sub L can equal negative L to positive L, including 0. So we're getting more possibilities here. Okay? So again, let's take an example. N equals 1. L has to be 0, which means I'm in the S orbital. M sub L has to be 0, which means I only can have one possible location because I only have one possible orbital that I can be in for the S. Okay? What happens when we get to n equals 2? Right? If I'm in n equals 2, then I could be in the S or the P. I could be 0 or 1 for L. If I'm in the P orbital, that will be a value of 1 for L, which means my possibilities here would be negative 1, 0, or positive 1 if I'm in n equals 2. Okay? And that should make sense because in the P orbital, or in the P sublevel, sorry, for over here, I have 6 total electrons that could be here. And if they're allowed to be 2 to a bed, so to speak, then I'm going to have 3 boxes here. 1, 2, 3 that can each hold 2 electrons. Or if you go back to the boarding house analogy, I have 3 sets of bunk beds that can each hold 2 electrons, or 2 people. So here, if I know I'm in sublevel P, now I want to know, well, am I in this box, or this box? And that's where the numbers come in for that. So come down to D. here. If I have now in D, I have 10 possible electrons to deal with here. But they can fit in 5 different beds. So I want to know if I'm in this bed, this bed, this bed, this bed, or this bed. Well, because D would correspond to number 2, right? L equals 2 down here. That means my possible values for D are -2, -1, 0, +1, +2. In other words, I have 5 solvable values, which is great because I have 5 possible boxes, 1, 2, 3, 4, 5 that I could be in, okay? And so on and so on, all right? Now, the last level of specificity is going to be the spin, okay? We simplify the spin, it's called M sub S, okay? And this is really just based on up or down. We have to assign a number to it, and so they just kind of arbitrarily decided that it's either +1/2 or -1/2 or up or down. You might just see it as positive or negative, but usually there's the number associated with it, okay? All right, so what does this mean and how do we use it? So I want to finish here with an application of this. So let's draw the orbital diagram for oxygen. So we're going to start with 1s, 2s, 2p. I'm going to go to the periodic table and find out that oxygen is number 8. So I have to put 8 electrons in here. So I'm going to go 1, 2, 3, 4. And then remember we go one at a time now. And then I now start to double up there. Okay? So that's oxygen's orbital diagram. So we want to be able to talk about these electrons individually, as in like one at a time. Okay? So I would like for us to describe this electron by using the 4 quantum numbers. So in other words, this. So we'd have the n value, the L value, the M sub L, and the M sub S. Right? So take a second, see if you can do that. Okay? I'm going to keep going, but if you want to pause the video to do it yourself, go for it. So, oxygen. This electron, start simple. What row on the periodic table is it in? Well, it's in energy level 2, so 2. Now, what section is it in, S or P? Well, we're in P, so we're going to be value 1. If we were in S, we would put a 0 there. Those are the only 2 options, though. Now, the M sub L value could be either -L to +L, so this would be -1, 0, +1. So which box are we in? We are in box 0. Which way is the arrow pointing? Up. Okay? Hopefully that makes sense. Now, I'm going to list some quantum numbers, and you're going to tell me which electron I'm referring to in oxygen. Okay? So I'm going to give you the quantum numbers. There. Tell me what electron I'm talking about. Okay. 2, so we're either in S or P. 0, which means we're in S. 0, because there's only one possible box that we're in, so we're in that box. Negative, down. So that's that one. Okay? That is quantum numbers in a nutshell. Okay, we're going to talk a little bit more about the shapes of these orbitals on Monday, but hopefully that gives you a good sense of where we're at. Okay? No homework for the weekend, but you can give a couple of the problems that are listed on the syllabus for today's class a try, and hopefully that will make sense. All right, have a great weekend.